Alright, welcome back. The next topic is how to tangle with piecewise functions. We haven't talked about piecewise functions yet. A piecewise function is often necessary to describe the way something behaves. Like, you may have fundamentally different behavior of a system, let's say for the first 3 days, than you do for the subsequent 10 days. Maybe you're looking at sales data before and after a competitor opens up. So you might be the only grocery store in town and you have a certain sales characteristic. And then one day a competitor opens. Your sales characteristic is going to be completely different. Any type of growth curve you had before is going to be replaced by a different curve, probably not growth. What I have shown here is a piecewise function with two pieces that touch. It's not necessary for both pieces to touch, it's just something that sometimes happens. This function f of x is equal to 500 plus 2x squared for x between 0 and 10. And then it's equal to 750 minus 5x for x between 10 and 150. Now that first part, the top part of the piecewise function, the part that corresponds to x values between 0 and 10, that might look familiar. That was from the beginning of the week of the antiderivative material kind of motivating antiderivatives, motivating the definite intervals rather. And it represented, the function represents how much money is in the account as a function of time if you increase the amount of money by $4 every day and start with $500. So you get the rate of change formula, so that's f prime of t, integrate it, use the initial condition to find c, and it gives you the top part of that curve. What's happening here is that is the first 10 days. Then after you put money into the account, you start taking money out. So this is a mathematical model of investing something into an account for 10 days, and then taking something out for the next 140 days, taking out $5 a day. A constant $5. So you're not taking out 5 and then 10 and then 15. It's just take out 5 and then 5 and 5. And this is what the graph of that bank account would look like. You couldn't possibly describe this curve, this shape, you couldn't possibly model this type of behavior with a nice smooth curve that wasn't a piecewise function. You might be able to get away with something like this. You might, if you were desperate, you might be able to do this. You might be able to do something like that. Would have that type of behavior. Maybe you may be able to make a model like this, or that type of behavior, but you wouldn't be able to get that type of sharp corner there. And it's even worse if there's a gap, if the pieces of the functions don't touch. So these are really needed. These functions really are part of your zoo of functions that you have to work with. They're necessary to describe normal things. In terms of integration, the key property that we use to integrate such nasty looking, but not that in reality, not practical reality, not actually that nasty function, is we use this method for splitting up an integral. We integrate from a to b as integral from a to c plus integral from c to b. We just take a pit stop. And we take the pit stop at the location where the piecewise function switches its behavior. So in this graph and in this function, the piecewise function changes its character at x equals 10. Change of character at x equals 10. And it's the same thing here. Change of piece at x equals 10. So we're going to use the location where the function switches its behavior, or switches from one piece to the other piece, to indicate where we should split up our integral. So in this first example, we're asked to find the integral from -3 to 5 of f of x dx. If f of x is equal to a piecewise function, where the first piece for x less than 1 is 6x squared, and the second piece for x greater than or equal to 1 is 20 minus 2x. So it splits at x equals 1. That means this integral is going to be the integral from -3 to 1 of f of x dx plus the integral from 1 to 5 of f of x dx. So it wasn't chosen randomly. We're not choosing just anywhere to split it. We're choosing where the piecewise function switches from one part to the other part. Now I'm going to substitute in the correct piece into the correct location. Between x equals -3 and x is equal to 1, what is the function? Well, inside that region, f of x is 6x squared. That's for the part less than 1. Then for the part larger than 1 in the second region, from 1 to 5, it's 20 minus 2x. We're going to take the antiderivative of each piece and evaluate. So the antiderivative of 6x squared is 6 times 1/3 x cubed, so 2x cubed, evaluated from -3 to 1. The second part, the antiderivative of 20 is 20x. The antiderivative of 2x is 2 times 1/2 x squared, which is just x squared, so minus x squared, evaluated from 1 to 5. And then we can plug in the bounds. So I have 2 times 1 cubed minus 2 times -3 cubed plus the top bound here, 20 times 5 minus 25. Subtract the lower bound, 20 times 1, subtract 1 squared, and then simplify. So 2 plus 54, 3 to the 3, 27, -3 to the 3, -27 times -2, positive 54. And then we have 100 minus 25, so 75. And then we have minus 19. So 56 plus, and then 75 minus 9, 66 minus 10, 56, so 112. And here's another example. This one slightly easier, even though it looks harder. We have the integral from 1 to 20 of h of x. Is what we're asked for. And what we're given is a piecewise function for h of x. H of x is equal to one thing, 12 over x squared, for x values between 0 and 4, not including 0. So we don't have a division by 0 problem per se. And then it's equal to g of x for x greater than or equal to 4. We also have information about the integral from 4 to 20 of g of x. We're told that that integral is equal to 10. So this function switches its character at 4. That means we have to split our integral at 4. So this is going to be the integral from 1 to 4 of h of x plus the integral from 4 to 20 of h of x. Next thing we do is we replace the correct function with the correct piece. So from 1 to 4, that's the top part of the piecewise function, which is in force between 0 and 4, which includes from 1 to 4. So we have 12 x to the power of -2, just thinking ahead. We're going to have to do that to take the antiderivative. And plus the antiderivative from 4 to 20 of g of x. All right, now we can take the antiderivative of the first piece using the anti-power rule. We'll have 12 times 1 over -1 x to the power of -1. And that's evaluated from 1 to 4. And for the second part, we can directly quote the number that comes out. It's 10. Okay. And now we're going to plug in the, so oh no. Okay, so I'm going to plug in the bounds. That 10, by the way, just I lost track of my thought there. That came from here. Interval from 4 to 20 was given to us. Okay, now we have to very carefully evaluate this function. So we have negative 12 over x evaluated from 1 to 4 plus 10. So that'll be negative 12 over 4 subtract negative 12 over 1 plus 10. So negative 3 plus 12 plus 10, which is 19. So the important thing when working with piecewise functions and integrals is to look at where the function switches and split your integral at that location. And in this problem we had an extra wrinkle of sorts, is we didn't know what g of x was, but we didn't need to. We were told what the integral from 4 to 20 of g of x was, and that was all that we needed. See you next time.